Good evening, everyone. In previous class, we were discussing about coordination chemistry. In today's class, I'm going to start the new topic that is the a block or length and ignite chemistry, right? And simultaneously, we will discuss the remaining part of the coordination chemistry. Okay. So today we will start a block chemistry or length and electronites. So we are going to start F block chemistry, right? Or you can say lanthanoids and actinoids, right? So, and along with the topic, we will also discuss the PYQs that has been asked in your examination, that is in UPSC. So now this is a block chemistry. Okay. Firstly, we must have the idea of the block elements, right? If we have a center, right, nucleus, and these are three cells. This is the outer cell. This is called ultimate cell. The outermost cell is called ultimate cell, right? And this cell is called penultimate, the second outermost cell. And this third cell is called anti-penultimate cell. Anti-penultimate cell, right? So, so if in any system, electron is going to fill in this anti-penultimate cell, for example, for F block elements, the filling of electron for F block elements, the filling of electrons like this, n minus 2f, 1 to 14, n minus 1d, 0 to 1, and ns2, right? So this is the ultimate cell, this is the penultimate cell, this is the anti-penultimate cell. So in any element, an electron is going to enter into anti-penultimate F subcell, then that element belongs to F block element. So what will be the definition? Elements in which last electron one, okay, one. Just a minute. Okay. Elements in which last electron enters into anti-penultimate F subcell are called F block elements, right? Now the F block elements have been divided into two categories, right? Here F block elements, two group, that is one is the 4F series that ranges from cerium to lutetium, right? 58 to 71. Okay. And the 5F series, this is from thorium to lawrencium. Okay, 92103. Fine. So there is also 14 elements in 4F series and also 14 elements in 5F series. These 4F series elements are called, they are called lanthanoids and they are called actinoids, right? Now, both the chemistry of lanthanoid and actinoids is less developed, right? Simple, we can write a line. The chemistry of both lanthanoids and actinoids is less developed, right? This is due to why the chemistry of lanthanoid actinoids is not as much broader as compared to that of D block complexes, right? This is because of following factors. First, in case of lanthanoids, right? In case of lanthanoid, we have 4F subcell, then we have 5D subcell, then we have 6S subcell. Then here is the X. X is the interacting species or ligand. This 4F subcell is present in very deep. Yeah, we can say it has deep buried nature, right? In case of lanthanoid, it has deep buried nature. If it has deep buried nature, it means this orbital has very poor interaction or very less interaction with X. So what we can say, the poor interaction between 4F orbitals and surrounding 4F orbitals and surroundings. So if there will be very poor interaction, then chemistry will be less developed. Simple interaction between 4F orbitals and surroundings, right? So why the chemistry is less developed? Because of deep buried nature of 4F orbital. So only one line you have to write, the chemistry of lanthonide is less developed because of the deep buried nature of 4F orbital, due to which, why deep buried nature? Because the first cell, in order to interact this X with the F orbital, it has to cross, yeah, it has to face the six subcell, a sixth cell, fifth cell, and then fourth cell, right? Now, in case of actinoids, the arrangement is similar like this, similar to that of lanthanoid, 5F, 6D, 7S. But there is one thing, the 5F orbital has more expansion as compared to that of 4F orbital. So here the concept of deep buried nature cannot be applied because 4F orbital have more extension as compared to that of actinoids. But the chemistry of actinoids is less developed because of what? All the actinoids are radioactive in nature. Why? All the actinoids are radioactive in nature, since they tends to decompose or degrade. They tends to show radioactive decay. Therefore, the compound that will be formed by the actinide will be less stable, right? And hence, in order to get the different kind of data or spectra from these complexes are less as compared to the of D block complexes. So why the chemistry of lanthanide actinides is less developed? In case of lanthanide, we can say this is deep buried nature. In case of actinide, we can say all the actinides are radioactive in nature. All the lanthanides are not radioactive in nature, right? Here you cannot apply the concept of deep buried nature because 5F orbital has more expansion as compared to that of 4F orbital because of more principal quantum number. And also there is the effect that is called relativistic effect that suggests that as the principal quantum number increases or as the mass increases, there is more expansion in case of D and F orbital as compared to that of S and P orbital. So in case of actinides, you have to write the all the actinides are radioactive in nature. While in case of lanthanoid, you can say it is very easy. The 4f orbital is present in D, therefore it has poor interaction with surrounding, resulting into the less development of the chemistry of this. Okay. Now, what we have to learn in case of lanthanoid actinides? We have to learn three or four major things in case of lanthanoid actinides, right? Uh, Lanthanide and actinides. What we have to learn? Some important properties, three or four properties. First, the most important property, the question that are asked from this topic is from the oxidation state and electronic configuration. Oxidation state, yeah, we can say electronic configuration and oxidation state for both lanthanide and actinides, right? Another thing is the lanthanide contraction or actinide contraction, lanthanide contraction and lanthanides and actinide contraction, right? Next thing is the magnetic property in case of both lanthanide and actinide, magnetic properties. Another thing is the color, most important part, color and electronic spectra. In question has been asked from these topics. We will discuss the PYQs, okay? Color and electronic spectra, and another thing that is important in case of lanthanide, the complex formation tendency, and also the separation of lanthanides and actinides, right? Mainly in case of lanthanides, because actinides are radioactive in nature, so they are formed by the radioactive decay, and it is very difficult to separate the actinides. In case of lanthanides are generally, you can say, except promethium are stable. Therefore, it is very easy. It is more easy. It is easy to separate lanthanides as compared to that of actinides. Now we will start with the electronic configuration and oxidation state. Firstly, we will learn about the lanthanide, then after actinides. Now the lanthanides, right? The lanthanides. You can say lanthanides. Okay. Now the lanthanides, the 4F series elements, 4F series elements are called lanthanides, right? Ranges from cerium 58 to lutetium 71, right? Earlier, earlier time, earlier lanthanides were called rare earth metals, rare earth metals. So, but nowadays, this definition is not appropriate or this terminology is not appropriate. That is it to call lanthanides as rare earth metal because they are found in a considerable amount. So we can here write nowadays, nowadays, yeah, in present time, we can say in present time, in present time, this terminology is not appropriate. This terminology is not appropriate. This terminology is not appropriate. Okay, so nowadays it is not good or not appropriate to call lanthanide as a rare earth metal. Okay, all the lanthanides are stable, right? All the lanthanides, all the lanthanides are found in nature, right? Among lanthanides, promethium PM. That is called promethium. This is radioactive in nature. Promethium is radioactive in nature, right? As it has no stable isotope. So what we have to remember that among lanthanides, the promethium is radioactive in nature and it has no stable isotopes. Other lanthanides are stable and other lanthanides are not radioactive in nature and they have stable isotope. Okay, no stable isotope, right? It is formed by radioactive decay. It is formed by radioactive decay. So this is all about the basic information of lanthanides. Now we are moving to the important part, that is the oxidation state and the electronic configuration. So here very important thing, the configuration, electronic configuration and oxidation state of lanthanides. So here we will write uh, element, here electronic configuration, here oxidation state, same element, here electronic configuration, and here oxidation state. Okay. Now I'm writing the name of lanthanides. Okay. L C S E G. Okay. G H E T Y L. Right here. E Y O R M. This is a trick, right? I will show you the mnemonics for this one. Okay. And the trick that I have learned is very, very difficult for you because I am I have practice of that one. So I will send you the trick that is more easy, as this trick I have learned in BSc, and so I am continuously using that trick. So it is very easy for us, very easy for me, but it will be very difficult for you. So I will send you the new trick. Okay? Now, what are the atomic number? The 57, 58, 59, 60, 61, 62, 63, 64, 65, 66, 7, 68, 69, 70, and 71. There is a homework that you try to find out the name of these compounds. Actually, lanthanum, cerium, promethium, neodymium, presiod- praseodymium, promethium, samarium, europium, gadolinium, terbium, dysprosium, holmium, erbium, thulium, ytterbium, and uh, lutetium. So I think this is homework for you, that try to name all these elements. What is the name of TB? What is the name of DY? What is the name of HO? Okay. Now the electronic configuration. Here we have xenon, right? It is a member of 5D series. So here 4F0, 5D1, 6S2. Here xenon 4F1, 5D1, 6S2. Here very, very important. 4F3, 5D0, 6S2. Here in case of neodymium, 4F4, 5D0, 6S2. Here in case of promethium, 4f5, 5d0, 6s2. Here 4f6, 5d0, 6s2. Okay. Usually it is 6s2. I'm not writing it. Okay. Here this is the 4f7, important 4f7, 5d0, 6s2. Here it is very important. Listen, this is a half field configuration. So here will be 4f7, 5d1. I'm writing with different colors. Okay. Here it is like this. 4f7, 5d1, 6s2. Why it is this so? Because this orbital is half filled. Therefore, the incoming electron is going into the 5d1. Okay. Now in the next one, this will be 4f9, not 4f9, 5d1, 5d0, 6s2. Why this is so? Because the addition of next electron will going to enter into 4f orbital and it will become 4f8. The 4f orbital is 4f8 configuration, not half filled. Is not half filled configuration. Therefore, the electron of 5d orbital is also going to enter into the 4f. Therefore, it is 4f9. So here, okay, actually, I don't have to write like this. Not like this is 4 4f9 5d0 6s2. Here 4f10 5d0 6s2. Here 4f11 5d0 6s2. Actually, there's no need to write 6s2, right? It is 6s2, okay? Now the 4f12 5d0 6s2, 4f13, right? This is like this, 5d0 6s2, right? Here also 4f14 5d0 6s2. Here 4f14 5d1 6s2. Okay, this is the configuration, right? I am making a important thing for this one. I will explain why, right? Now, and also I will explain why the configuration in cerium is 4f1 5d1. Well, in case of praseodymium, all the electrons are going to enter into the 4f3. Okay. Now the xenon is 54. Okay, the 54 and 53, 57. Now the oxidation state. Okay, the common oxidation state for most of the lanthanide is here the plus 3, here the plus 3 and plus 4, here also plus 3 and plus 4, here also plus 3 and plus 4, right? Here in PM, this is the plus 3, here samarium plus 2 and plus 3, here also plus 2 and plus 3. Now here plus 3, then plus 3 and plus 4, plus 3 and plus 4. Now the plus 3 mainly, plus 2 and plus 3, plus 2 plus 3, and plus 3. So the most common oxidation state for lanthanide is plus 3. That is common for all the lanthanides. How will you remember the oxidation state? Listen, above the half field, above the half field, this 4f7 plus 2 and plus 3, and also above this 4f14 5 full field plus 2 plus 3, right? Now, where 4f7 below the 4f7, this is the plus 3 and plus 4. Below the 4f0, this is the plus 3 and plus. Means when we have 4f7 and 4f14, then above that the oxidation state is plus 2 and plus 3. When we have f0, f7 or f14, then after element coming after those configuration have plus 3 and plus 4 oxidation state. Right? Listen, f0 and f7 plus 3 plus 4 plus 3 plus 4, f0 plus 3 plus 4. f7 above plus 2 plus 3. Above means before plus 2 plus 3 plus 2 plus 3. f14 fulfilled above plus 2 plus 3 plus 2 plus 3. Okay. Now here it is clear that the most common and most of, listen one thing very carefully. As we are we are going to see, or we are seeing that, or it is clear from this this oxidation it is clear from the slide that the lanthanides are showing the different oxidation state, but all the lanthanides means starting from the cerium to lutetium, all the lanthanides are the most common and most stable oxidation state is +3. The lanthanides which have +2 oxidation state along with +3, lanthanide which has +4 oxidation state along with +3 is less stable. So what we have to write? The most common and most one very important thing, right? The most common and most stable, right? The most common, the most common and most stable oxidation state, oxidation state for all the lanthanoids is +3, right? There are many lanthanoids, and this is the about oxidation state. Now, why the oxidation state in cerium is, listen, in case of cerium, the arrangement of electron is like this: 4f1, 5d1, 6s2. Very, very important. Why this is so? Because in initially, why the electrons are present in the 4f orbital? Listen, the 4f orbital, yeah, we can say the f orbitals has more expansion as compared to d orbital. In initial stage, the energy difference between 4f and 5d orbital is less. So in this case, in case of cerium, the energy difference between 4f and 5d is less. Yeah, I can write it in this note. Yeah, we can say less energy difference. Less energy difference between 4f and 5d. Therefore, due to which the energy difference between 4f and 5d is less, then electron can occupy both these orbitals, this one and this one. Okay. Hence, both 4f and 5d orbitals are occupied. 5d orbitals are occupied. Right? Below cerium, there is element called PR, praseodymium. In case of praseodymium, what is the problem? Well, in case of praseodymium, we have xenon 4f3, 5d0, 6s2. Why 5d orbital is vacant? It is 58. It is 59. Why? Because on moving from 58 to 59, there is increase in proton number, right? Increase in proton leads to increase in nuclear force, right? Right? Nuclear force will be more effective over the 4f orbital as compared to 4f orbital, because 4f orbitals are present more closer to the nucleus, right? Right? 4f orbital is present in 4 cell, 5d orbital is present in 5th cell. So the nuclear force will be more over the 4f cell as compared to 5d cell. Therefore, in this case, the energy difference means this orbital is attracted by more force, this orbital is attracted by less force. Therefore, there will be energy difference. So we can say that energy difference is more, right? That is the 4f orbital have low energy, much low energy as compared to 5d orbital which has high energy. Therefore, this orbital is occupied and this orbital is vacant. Okay. Is initial stage the energy difference is less because the nuclear force is less. You can say how it is possible that increase in one proton leads to energy difference between 4f and 5d orbitals, so that the electrons are going to occupy only the 4f orbital. Actually, this process is starting from the lanthanum also. Okay, so this is not the change on going from cerium to praseodymium is not in a single step. Actually, the energy difference between 4f and 5d orbital is started from the lanthanum and other elements, other element, that is element before the 57. Here, this effect is dominated. Therefore, 4f orbital, the energy difference between 4f or 5f orbital is such that the energy of 4f orbital is much less as compared to 5d. Therefore, electrons are going to enter into low energy orbital, that is 4f orbital. Okay. Now the electronic configuration in case of gadolinium. Gadolinium important. Gadolinium we have 64. We have xenon 4f7 5d1 62. Why the electron is present in 5d orbital? Because the 4f7 orbital has half filled configuration, right? Half filled configuration, and it is a kind of stable configuration. So in order to maintain stable configuration, the electron is going to enter into 5d orbital, stable configuration, right? So this is, and why the, in case of TB, the 5d orbital is vacant because on going from gadolinium to TB, the next electron will enter into 4f orbital, then it will become 4f8 and it will become 5d1. But this arrangement is less favorable because the 4f orbital is now partly filled, not half filled. Why this arrangement is favorable? Because this orbital is half filled. But the addition of next electron make this orbital to be partly filled. That is, it will, this arrangement will be less favorable. Hence, electron is not going to enter into 5d orbital. It will remain in 4f orbital. Therefore, TB or terbium has 4f9 5d0 6s2, not 4f8 5d1 6s2 configuration. Okay. Now, this is all about the electronic configuration. Okay. Now, along with plus 3 oxidation state, there are many lanthanides who also show the oxidation state like plus 2 and plus 3, right? Along with plus 3 oxidation state, many lanthanides also show plus 2 and plus 4 oxidation state, right? Here, in case of plus 2 oxidation state, in case of plus 2 oxidation state, yeah, we can say among plus 2 oxidation state, the stability order is stability order is, it is like, it is the most stable is U2 plus, then YB2 plus, then SM2 plus, and then TM2 plus. This is the stability order of plus 2 oxidation state in case of lanthanide. Stability order in case of stability order of plus 2 oxidation state. Okay. Why plus? Now we will explain why the stability of europium 2 plus and YB2 plus is more as compared to that of SM2 plus and TM2 plus. In case of uh, in this case, EU2 plus YE2 plus is stable. The EU2 plus is configuration xenon 4F7 5D0 6D0 as configuration for europium is xenon 4F7 5D0 6s2. So when europium so plus 2 oxidation state, half filled it has half filled F7, half filled F7 state. But in case of YB2 plus, the configuration for YB2 plus is xenon 4F14 5D0 6D0. It has fulfilled F14 state. So in case of europium 2 plus, in case of YB2 plus, these oxidation states are stable as they have more stable configuration as compared to that of SM2 plus. Why more stable? Because half fill configuration, it is full fill configuration. In case of samarium and TM, samarium 2 plus and TM 2 plus, here you can see the oxidation state, you can see the electronic configuration. In case of samarium, we have 4F6. In case of TV, we have 4F9. Sorry, in case of TM, we have 4F13. So here, in case of samarium, we have 4F6, 5D0, 6S2, sorry, 6S0. Here we have 4F13, 5D0, and 6S0. So they have partly filled configuration, partly filled configuration, hence less stable. Okay. So this is the stability order for +2. There are some other things. Actually, the stability of any system is not only based on the electronic configuration, half-filled or full-filled configuration. It is basically based on three factors. First is heat of atomization factor. Second is the ionization factor. Third is the energy of solvation. But I am not going to explain all these things because it will be little bit difficult for you. Actually, it is easy, but it will take more time. So it is very easy for you to remember this. If any one of you want to more knowledge about that, you can ask me personally. Okay. So it is very easy to explain on this basis, right? So it is the europium 2 plus, YB2 plus, SM2 plus, and TM2 plus. Every +2 oxidation state, as we have seen earlier, that in case of all the lanthanide, the most stable oxidation state is +3. It means the Ln2 plus ion, that is lanthanide +2 oxidation state, has tendency to convert into +3 because the most stable oxidation state for lanthanide is +2. It means all the Ln2 plus ion have tendency to get oxidized, right? That they have tendency to get oxidized, right? And any system or any species which have tendency to get oxidized, it behave as reducing agent. It means all the Ln2 plus ions are reducing agent. What does it mean? It means all the Ln2 plus ions behave as reducing reducing agent. What will be the order of reducing power? Listen, the lanthanide which has least tendency to convert into +3 oxidation state has least reducing power. Lanthanide which has highest tendency to convert into +3 oxidation state has highest reducing power. Or we can say that the most stable Ln2 plus ion most stable Ln2 plus ion will have least reducing power, and least stable Ln2 plus ion will have most reducing power. So we can write here the reducing power, the Tm2 plus, Sm2 plus, Yb2 plus, and U2 plus. This is the reducing power of lanthanide, the reducing power of Ln2 plus ion. This has the highest reducing power. Why this is so? Because the +2 oxidation state of europium is most stable. Therefore, this uh, it has less tendency to get converted into +3 oxidation state. It means it has less tendency to get oxidized as compared to Tm, Sm, Yb. It means it has least reducing power. While in case of Tm2 plus, Since Cm2 plus is least stable, means it has more tendency to get converted into plus 3 oxidation state. It means it has more tendency to get oxidized and more tendency to produce electron. Therefore, it will have highest reducing power. Okay. So this is all about the plus 2 oxidation state of lanthanides. Now, so one more important thing among lanthanide we should learn. Actually, there are some questions. Listen, if we are given with a complex like LaI2, GDI2, LuI2 like this, right? These are the diiodides of lanthanides. So in case of LaI2 plus, we can write it like this: La2 plus and 2I minus. In case of GDI2 plus, we can write it like 2I minus. Here we can write it like Lu2 plus and 2I minus. But this is incorrect. Why? Among La2 plus, among lanthanum, gadolinium, and lutetium, right? None of these lanthanides are going to show plus 2 oxidation state. They show only oxidation state that is plus 3. It means this complex or this compound is like this: La3 plus 2I minus, right? The two electrons of lanthanum is taken by iodine to get converted into iodide ion. The one electron remains as free. Similarly, in case of Gd2 plus, it is Gd2I minus free electron. Similarly, in case of lutetium, it is lutetium 2 plus 2I minus and free electron. So the compound like LaI2, GDI2, LuI2, the actual arrangement of ion is like this. Since all these compounds have free electrons, right? And as we know, the free electrons are found in metals. Therefore, they behave or they has these complexes. They have metallic luster, right? So they have free electron, and also we have as metallic conductor. So these compounds of lanthanides are metallic conductor. Okay, these diiodides are metallic conductor because the oxidation state of lanthanide is not plus 2, it is plus 3. For gadolinium, lanthanum, and lutetium, these these metals do not show plus 3 oxidation state. They have as metallic conductor. So question can be asked, explain why the GDI2 plus and Le2 plus I we have as metallic conductor. So you can say in case of GDI2 and LuI2 plus, the oxidation state of gadolinium is plus 3 and the two electrons of gadolinium is taken by iodine to get converted into 2 iodide minus, and third electron is present as free electron. If any system has free electron, then we have as metallic conductor and it will has metallic luster, right? So this is all about the now, one another important thing related to the plus 2 oxidation state is that two metals like europium 2 plus and Yb2 plus, as these two metals as most stable, they are these plus 2 oxidation state of lanthanides are most stable, right? These metals shows similarities in properties with right properties with properties with alkaline earth metals, right? Why? Reason is an heavier alkaline earth metal. First is the both both means this europium Yb and alkaline earth metal. Both have larger size, right? Common plus 2 oxidation state. That CFSC is nearly zero. CFSC in case of alkaline earth metal is nearly zero. In case of EU2 plus YB2 plus is very, very less. Why very, very less? Because 4f orbitals are present in D, therefore they have poor interaction with the surroundings. So why the properties of lanthanides, and lanthanides means lanthanides like EU2 plus, right? These two lanthanides and the properties of heavier alkaline earth metals are similar because they have larger size. They have common plus, they have stable plus 2 oxidation state, plus 2 oxidation state and stable oxidation state, right? CFSC in case of length alkaline orbital is zero because there is no splitting of s orbital. Yeah, of course, f orbitals are going to split, but the interaction between 4f orbital and surrounding is very, very less. So the CFSC value is very, very low. It means they don't have any role in deciding geometry, properties, color of the lanthanides. Okay. So all these, because of all these parameters, because of all these similarities, they have similar properties. Fine. Fine. Okay. Just a minute. Okay. 1 minute. Now, so this is all about the plus 2 oxidation state of lanthanides. We have seen the stability of plus 2 oxidation state. We have seen the reducing power of plus 2 oxidation state. We have seen the properties of similarities in properties of uh, uh, lanthanides, that is europium and YB2 plus, along with the alkaline earth metal. What are the properties that are similar? We can here write. We can write similarities among EU2 plus, YB2 plus, and heavier alkaline earth metals. The first and most important similarity, because of these things, there is similarity, right? The most important similarity is EUYB, like alkaline earth metal, that is heavier alkaline earth metal, like calcium, strontium, and barium, show blue color in liquid ammonia solution, right? Alkali metals and heavier alkaline earth metals show deep blue color in liquid ammonia solution. Similar kind of color is shown by U and Y. Why this is so? Because of these similarities. The another similarity is that both the sulfates of BaSO4, sulfates like, right? Sulfates like, yeah, BaSO, right? The sulfates like BaSO4, EuSO4, YbSO4 are insoluble in water. Sulfates of these metals are insoluble in water. Insoluble in water. So it is very important, right? So we have seen that some lanthanides will plus 2 oxidation state, We have seen the order of stability of oxidation state. We have seen the order of reducing power. We have seen that europium 2 plus and yb 2 plus are the most stable plus Ln2 plus ions, and these Ln2 plus ions show similarities with the heavier alkaline earth metal because both heavier alkaline earth metal as well lanthanides are of larger size. They have plus 2 stable oxidation state, and also there is no role of coefficient deciding geometry in both the cases. Because of this, they show simulating properties. The simulating properties are like European YB show blue color, like blue color in liquid ammonia solution, as that as shown by the alkaline earth metal, and also sulfates. The another similarity we can see that we can show that the sulfates of barium sulfate, sulfates of barium, sulfates of europium, sulfates of ytterbium are insoluble in water. So these are the similarity of European YV with the heavier alkaline metal, right? Now we are going to move the another oxidation state, this is plus 4 oxidation state of lanthanides, right? Uh, in case of plus 4 oxidation state of lanthanides, listen, the plus 4 oxide the plus 4 lanthanides have tendency to get converted into plus 3. Why? Because the most stable oxidation state for all the lanthanides is plus 3. Either it's to plus 4 oxidation state or it's to plus 2 oxidation. So it has tendency to get reduced. So all the Ln4 plus ion has tendency to get reduced. Yeah, we can say tendency for reduction, right? Reduction means they behave as oxidizing agent. So here we can say that all the Ln4 plus ions behave as oxidizing agent, right? Stability order of stability order of Ln4 plus ion is can be given as, here we can write the stability order for Ln4 plus ion. One minute. It is like cerium 4 plus, the Tb 4 plus, Pr 4 plus, neodymium 4 plus, and Dy 4 plus. Here you can write, you can easily understand this stability order. In case of cerium, we have 4F0, 5D0, 6S0 configuration. So it has actually noble gas configuration. Cerium 4 plus has noble gas configuration. Therefore, it is the most stable. So this is the most stable plus 4, right? And this TV4 plus has xenon 4F7, 5D0, 6S0. It has half filled configuration, and other members have partly filled configuration. So they are less stable. Actually, I am telling you again, the only reason for explaining the stability of oxidation state is not the electronic configuration. I am writing is because I am telling you this because the stability of oxidation state is basically depend upon following three factors. Three factors. First is the heat of atomization, that is the endothermic process, atomization. Another is the ionization energy. These three factors, ionization energy, and third is the both these are the endothermic process endothermic process. And the last one is the solvation energy. Either you can say in case of aqueous medium, it is hydration energy. This is the exothermic process. So the stability of oxidation state is dependent on following parameters, right? Not on the electronic configuration, but all these factors are experimental. Value of heat of atomization can be obtained only by experiment. Value of ionization energy can be obtained only by experiment. Value of the solvation energy can be obtained only by experiment. So none of these three parameters can be explained theoretically, right? Theoretically, we can explain we can suggest the stability of configuration. Therefore, listen, if you want to predict the stability of any oxidation state in any solvent, you have you should have the idea, or you should have the values of all these parameters. Then you will be able to predict the stability of oxidation state. Here I am writing the stable configuration, half-fill configuration to make you easier, right? This parameter, that the by knowing this configuration or stable configuration or half-fill or full-fill configuration to predict the stability of oxidation state is not always true. I am repeating it again. I am telling that explaining the stability of any oxidation state only on the basis of stability of configurations is not always true. It is true when we have the knowledge of heat of atomization, we have the knowledge of ionization energy, we have the knowledge of solvation energy, and all these parameters are experimental. Therefore, in most of the cases, we try to explain the stability of oxidation state on the basis of stable configuration. But the explaining the stability of oxidation state of any system on the basis of stable configuration is not always true, right? So it is easy to explain by this method, because we must have for the knowledge of this one, for the knowledge of this one, for the knowledge of this one, we must we have to do the experiment, and that an experiment cannot be done by us because we are studying is theoretically. So try to learn it, right? The order of cerium TB. In case of cerium, it is very easy because noble gas configuration is the most stable configuration, so most stable, and TB2 plus is less stable configuration, so less stable ion, right? The stability of these three ions have particle configuration, therefore they are less stable as compared to that of cerium and TB. But you want to explain the exact order why PR4 has PR4 plus has particle configuration, neodymium 4 plus also has particle configuration. So why it is more stable, why it is less stable? In order to explain these things, you must have the knowledge of all these experimental values. So it is better to learn this, because in examination you don't have time to remember the numerical values of these three: these heat of atomization, ionization energy, and solvation energy. Right? Now, as we know, this is the stability order of plus 4 ion, and among these, the most important is the cerium 3 plus. The cerium 3 plus, this exists in aqueous medium, right? Yeah, stable in aqueous medium. While other Ln4 plus ions, other Ln4 plus ion are not stable in aqueous medium, are found in form of fluorides and oxides. Why this is so? Because water is weak ligand. Yeah, water has less interaction with the ion as compared to that of oxide and fluoride, right? Therefore, listen, one thing I will explain you in one class: how to predict the stable oxidation state, how to predict the more stable oxidation state, how to predict the less oxidation state, why the metal ion with some surroundings so less stable low oxidation state, while with other surroundings metals or central atom is going to show high oxidation state. Listen one thing very carefully. In any system, the highest oxidation state or higher oxidation state are stabilized by ligands like fluoride and oxide. Why? Because if you want to achieve the higher oxidation state, then there is requirement of removal of more number of electrons. More number of electron will require more energy. right? It means the process will be more endothermic, right? In nature, those processes are feasible in which the energy required to achieve any particular process is compensated by any means. What I am saying, if we want to get cerium plus 4 ion, then we have to remove 4 electrons from cerium, right? So the cerium plus 4 oxidation state will be stable only when cerium is going to interact with any ligand, so cerium 4 plus is going to interact with any surrounding, or cerium 4 plus is going to interact with any solvent, then interaction energy of cerium 4 plus with surrounding or solvent should be such that it will be able to compensate the energy required to get cerium 4 plus, that is energy required to remove the 4 electrons from cerium. Then cerium 4 plus will be stable. If the solvation energy or the bond formed by cerium 4 plus with any surrounding is less that the energy required in order to achieve cerium 4 plus, that is the first ionization, second, third, and fourth ionization energy, then cerium 4 plus in that condition will be less stable. Means whatever the energy is required in order to achieve that particular oxidation state, that particular oxidation state will be stable only in that condition, the condition where the interaction will generate the energy that is required for generation of that ion. I am going to make it more easier. For example, we have cerium and I am going to convert into cerium 4 plus. Okay. So 4 electron means first ionization energy, second ionization energy, third ionization energy, fourth ionization energy, right? And I am making cerium CCl4 and I am making CeF4. This is unstable, this is stable. Why? Because fluorine has a smaller size, it will make a strong bond, hence more energy is released. More bond energy matlab more energy is released. For example, uh, we can say A, right? So here this A energy either should be equal to I1 plus I2 plus I3, or A should be greater than I1 plus I2 plus I3 plus I4. In this case, stability will be there. In this case, there will be equilibrium condition, right? If condition is like this, the energy required in order to achieve the plus 4 oxidation is more as compared to the energy released from bond, then this will be less stable. In case of Cl, it is of larger size, weak bond, less energy, right? Here B, and B is less as compared to I1 plus I2 plus I3 plus I4, hence it is not stable. So cerium CeF4 is stable. Why CCl4 is not stable? Right? On the basis of this parameter, you can explain the stability of PR, neodymium dy4 plus. So in any system, if you want to make stabilize a higher oxidation state, then surrounding will be such that they form surroundings should be such that they form bond of such a strength that will be stable to satisfy or neutralize or compensate the energy that has been consumed in order to explain that high oxidation state, right? So if you read any textbook, then you will find that in any system where central atom is of higher oxidation state, then most common surroundings are either fluoride or oxide. Why? Because size of fluoride and oxide are smaller, therefore they will form more stronger bond, hence more bond energy, and that high bond energy is going to that high bond energy is going to make stable that high oxidation state. Okay. Now we can also write here the uh, oxidizing power of Ln4 plus ion. Oxidizing power of Ln4 plus ions. The most stable Ln4 plus ion will has the most stable Ln4 plus ion will have least oxidizing power, and least stable will have most oxidation. Cerium 4 plus, Tb4 plus, Pr4 plus, Md4 plus, Dy4 plus. This is the oxidizing power. Since Dy4 plus is least stable, it means it has most tendency to accept electron to get converted into plus 3. Cerium 4 plus is most stable, it means it has less tendency to get converted into plus 3. It means it has more tendency to accept electron, it has less tendency to accept electron, so it will have more oxidizing power and it will have less oxidizing power. So this is all about the electronic configuration and oxidation state of lanthanides, stability of plus 2 oxidation state, stability of plus 3 oxidation state, right? In this class, we will learn about the magnetic property, color and electron spectra, as well as lanthanide contraction. Okay, so this is all about the today's class, and in this class, we will learn about the lanthanide contraction. We will learn about the magnetic property as well as color and electron spectra of lanthanides.